Okay, I think this is the last talk of our session. I set up everything correctly. Could you please check that in Zoom? You can see my face and also the screen. And I also hope that my computer will not die from such number of connections. So my name is Grigorii Likhachev. I'm a postdoc in the group of Tobias Kippenberg, and I also was a cameraman the last 3 days. So in this talk, I would like to discuss applications of Soliton Microcombs, which were developed in the last decade, and in particular, Soliton Microcombs for coherent sensing and LiDAR. As you know, there was a pretty successful decade for silicon nitride and optical microcombs in general in the last 10 years. So I will briefly show main achievements of our group, but also other groups. So for the silicon nitride-based integrated photonics, several milestones. First of all, photonic damascene process for silicon nitride, which allowed us to fabricate thick waveguides with a waveguide thickness of more than 800 nanometers without cracks, with a high Q. And we were able to achieve anomalous dispersion required for the bright Soliton generation, as we heard many times during this last 3 to 4 days. But then more recently, we were able to co-integrate the piezoelectrical actuators on top of the same silicon nitride wafers to allow fast and linear actuation. And even more recently, we were able to implant erbium ions inside silicon nitride waveguides to allow the erbium gain on chip. And in collaboration with other groups, we were able to do the 3-5 co-integration on the same wafer, and Tobias and others, they offer thick and thin silicon nitride as a source. Some time ago in our group and in many other groups, lithium niobate was investigated in combination of silicon nitride via heterogeneous wafer scale bonding to allow the electro-optical tuning, not piezoelectrical, but electro-optical tuning, and with transient printing technique or wafer scale integration technique, 3-5 bonding were realized to allow photo detection or light generation. So here the overview of the Soliton Microcombs applications. Some of them, they followed the path of fiber laser, mod-lock laser comms. Some of them were really new and very relevant to Soliton Microcombs. So in the order of appearance, I think the main motivation was to use the optical frequency comp in Soliton regime as a frequency ruler, because the lines are well precise, and if you do self-reference and if you stabilize repetition rate and FCO, then you can indeed use it as a precise ruler to measure optical frequency. And this demonstration was done in 2017 and 18 as a part of DARPA program. Several groups, they demonstrated complicated system which consists of silicon nitride comp with a terahertz spacing and additional comp from silica toroid resonator with 20 gigahertz spacing. They both were locked. The terahertz spacing, terahertz comp was broad enough to do self-reference, and the small FSR comp was used as a finer grid. And the main demonstration was to measure the frequency of the laser, which is also on chip, to very high distance. Then in our group, in collaboration with other groups, we use independently. We use Soliton Microcombs as a source of microwave low noise signal, just by sending comb lines to the fast photodiode and using the output of the photodiode as a microwave source. Several applications of microcombs in coherent communications were demonstrated, and also in ultra-fast distance measurement, both in time-of-flight approach and also in frequency-modulated continuous wave approach. In the similar sense, optical coherence tomography might be seen as FMCW LiDAR, but with a much broader tuning range. Another very well-known application is dual comb spectroscopy to do the spectroscopy of absorption features, but now using our microcombs. I'll touch this a bit later. And a very interesting application, which is which our microcomp suits really well, is calibrate the shell spectrometers, which requires around 10 gigahertz mostly. So I will briefly comment on some of them. So in the telecom experiment, which our group and the group of Christian Kos and KT did quite a long time ago, we replaced many lasers for individual channels with a single Soliton Microcomb device and use many comb lines instead of individual lasers here to do the standard telecom experiment with a 75 kilometer delay and up to 34 terabits per second. So this result was improved several times by other group using not only comps in anomalous dispersion regime, but comps in normal dispersion regime, and more recently with the comps with a high conversion. So for the microwave generation, we use the rings with a pretty large radius to achieve either 10 gigahertz or 20 gigahertz free spectral range. We use the external CW laser to pump that, and then the output of your comp is sent on the post diode, and then the repetition rate is a source of a good, relatively good microwave. Here we measured the microwave properties, the single sideband phase noise, and you can see that it reaches values of minus 150 dBc per hertz at offsets above 1 megahertz. More recently, many groups, they significantly improved this result for microwave generation, but by using more complicated technique. The best results are achieved with the optical frequency division technique. It's basically use two very good lasers stabilized maybe with self-injection locking technique, which Andrei showed you in the previous talks. And then you place one laser maybe here and the second laser around here, and then you again measure you do the PDH locking of both lasers to your comb lines to respectful comb lines, and then you measure again the repetition rate, which is again the source of your microwave signal, and then it's improved by the factor which is proportional to the number of comb lines between your two lasers. And by doing this, now the results from teams from United States is around minus 145 dBc per hertz at offsets as low as 10 kilohertz and minus 135 dBc per hertz at offsets around 1 kilohertz, which is really good values, which beats most of the previous demonstration, except of some demonstration with the manual comp, fiber laser comp, but it's about the system, and now they have most of their components on chip. So a microphotonic astrocomp, this demonstration was done 5 years ago by our group in collaboration with Tobias Her group and also a group of Tobias Kirivahala in Caltech. So the idea here that we use again our microcomp just as a optical reference with a precisely fixed frequencies and well-defined frequencies, and we use it as a calibration tool to calibrate the shell spectrometer. So most of the shell spectrometers, they work at the visible wavelength, but there are also spectrometers which work at our wavelength range around telecom. And here you see the shell spectrograms. They are just stacked basically 2D spectrograms, and each vertical slice is a frequency around some values with 10 gigahertz space. And historically, they use some sort of mercury lamps and other type of sources with identified frequencies. Then now they use mode-locked fiber lasers as a calibration source, but they have a huge challenge that you need to filter out all the lines, because here the grid is 10 gigahertz. And our Soliton microcombs from microresonators can be easily adjusted and fabricated for line spacing of 10 gigahertz. That's why, and also our devices are comp. That's why it's very promising application for kind of scientific and technological application of Soliton microcombs.
This application is important that you have here a lot.
Not really. So of course it's better for them to use the precise rule. But even if we maintain the spacing, if the web rate is stable and FCO is stable within like known limits, 10 megahertz or below, it's still quite good. So it's better than to use some sort of gas lamp to do some sparse calibration. And why do you need it? You need it, for example, to detect the Doppler shift from some planets rotating around some stars, where the Doppler shift needs to be measured precisely on some of these frequencies. First demonstration of range in time-of-flight approach was done by, again, Christian Kos and our groups in 2007, where we use one local stimulator comp and one comp as was sent to the target. And here, the flying bullet was measured from the air gun with a comp. So, and actually it was even not just the presence measurement, it was a profiling of the bullet shape, which is realized. But the drawback here that in this approach, in the time of flight with two comps, the disambiguity range is very, very small because the pulse repetition rate is huge. So, and you can't distinguish between this pulse and the next pulse. That's why you can, in principle, measure distances only very close to the polymer. There are some tricks how to solve it, but in fact, there is a big limitation. For the spectroscopy, so I'll spend some time discussing spectroscopy. So this work from Kiri Vahala demonstrated dual comp spectroscopy following the method demonstrated a long time ago in the fiber laser community, model laser. So you have first comp and the second comp, which have slightly different FSRs. And then you use one comp as a local oscillator, the second comp, or in this configuration, you can mix them both and send through your absorption feature, so the test sample. And then you, by using the second comp as a local oscillator and you put the fast photodiode here, you map your optical frequencies to RF domain, and then you actually measure your absorption features not optically, not with the optical spectrometers, but in RF domain with electrical spectrum analyzers, which are much faster, and you can do acquisition at a much faster rates. Here you need to be careful. You need to be careful with the FSR difference to be able to use kind of not very fast photodiodes. So there is a trade-off about your bandwidth of the photodiode and the measurement speed always. But here they were able to do the HCN cell at high pressure measurement. However, the resolution, because there is no scanning path, you send only, you don't scan in frequency. So you send the comp as is with defined frequency. So you can resolve absorption features which are on of an order of your FSR. So in this case, they use FSR of 10 to 20 gigahertz. So that's why you can only resolve kind of broad absorption features in RF domain. It can be solved by scanning the full comp, which in the later years has been demonstrated. So I will show you our work from 2018 done by Erwin Lucas, which use kind of simpler system, and it has much better, much higher intrinsic and mutual stability, and it's compact, and it uses single resonator. So in this case, we go back from silicon nitride ring resonators to the elegant Western gallery mode resonators made in crystalline material, in this case magnesium fluoride. You can see that it's a polished cylinder and the optical field is around this circumference. There is protrusion with a pretty large radius, and this is the field distribution. And these resonators can support many mode families. Some examples are provided here. So not only in the radial direction, but in the vertical direction, you can excite very high Q modes, and typically many modes are really high Q of an order of 100 kilohertz intrinsic kappa, intrinsic cavity loss. And we observed that several mode families can support soliton formation because they're high Q and the coupling is pretty good. And the nonlinear coefficient of magnesium fluoride is low, but because the Q is 10 times higher, it's still doing it. So, and we pursue the experiment where we pump simultaneously two solitons in one resonators and a different spatial mode families. So the polarization is the same, but the spatial distribution of modes is different, and we pump them simultaneously, but not with the two pumps, but with a with the one pump and one pump derived from the first laser by using model. And in this case, if you have, and of course, different mode families, they have different spectral range, pre-spectral range. That's why you always have some Soliton, for example, with 12 gigahertz, and then another mode family with Soliton, which has slight change in your recognition rate. In this case, we considered both co-propagating and contra-propagating direction. So in the first demonstration, both Solitons, they moved, for example, counterclockwise in your cavity, as depicted here. So what is the experimental setup? You use single laser, then you use a single sideband modulator, electro-optical modulator, to generate your laser and then your sideband in the same fiber. And then you pump through the one tapered fiber, which we use as a coupling element, the resonator. And then in the output, you can detect optically the both comps simultaneously, and on ESA, you can measure the signal between them. What are the drawbacks of this scheme? That you cannot separate them. So they both generated in the same direction. You cannot separate them easily, and of course they interact with each other because there is non-zero overlap in the eigenmodes. That's why you observe some of it. This is the experimental result. So in fact, this optical spectrum consists spectrums of both solitons. So the black envelope is soliton number 1, and the red envelope, which you can also resolve if you look at the final grid, soliton number 2. So they both generated in the same resonator, and they're moving in the same direction in a different mode families. And then if you send the output to the photodiode, you can measure the beautiful comp in the RF domain. So the central frequency here is 4.2 gigahertz, which is frequency difference between your resonances of different mode families. So they are separated by fabrication around 4 gigahertz. And the FSR difference is only 600 kilohertz. So the Soliton 1 and Soliton 2, they have FSR difference of 600 kilohertz. And you can see that basically you reproduce, you map your optical spectrum to a RF domain. And of course, here at 4 gigahertz, you can measure really fast with a fast oscilloscope. And the mutual stability is excellent because we use same pump, and the modes are very close to each other. So the thermal noises are also correlated. That's why the individual comb line is not resolved by our ESA, so it's below 100. So it's excellent. The mutual, so the jitter in optical domain is pretty large. It's the same as your pump laser, but the mutual stability is excellent in this case. Next, we demonstrated contra-propagating because there is disadvantage in co-propagating that you cannot separate them and use them separately. In a contra-propagating scheme, you need to split your pump, your laser in both arms. You use the single sideband modulator to do the pump, and then you use 90% of this arm. Then you send via 2 circulators to your cavity. So the drawback in this scheme that you need 2 circulators from both sides, to pump from both sides. Then you can post amplify, you filter out, and then you have independent comps, counterclockwise and counterclockwise in both arms. And in principle, you can use them separately. And here the main experiment on the spectroscopy is very simple. So this is again optical spectrum for the blue, which is contra-propagating, and for the red and contra-propagating, here we hit some other combination of mode families. That's why we have some nasty dispersion rate, because our whispering gallery mode resonators are multi-mode, and it's much easier to hit these avoided mode crossings and generate some dispersive wave. That's why the spectrum is not as flat, but still it's enough to do some useful experiment. And this is RF spectrum. In this case, the FSR separation at 370 kilohertz. We use some different combination of families, mode families, and the pump difference is 2 gigahertz. That's why the RF comp is centered at 2.7 gigahertz, and the spacing is 370 kilohertz. And then in one arm, we sent only, for example, this we call a signal, and this we call a local oscillator, and then we only send signal through our absorption feature. We didn't use a gas cell, we just used the wave shaper to programmatically set some absorption feature with a known position and known width in optical domain. And then you combine them both on the reference arm and signal arm, And in this case, okay, this is local Soliton, this is signal. And what you can do, you can, because of the independent control of this comp and this comp, you can do phase result. So you can acquire both and also very fast because it's not optical measurement. Now it's measurement in the RF domain after fast photodiodes. So you can do it at, in this case, basically this 400 kilohertz rated. So these are the amplitude of your absorption features, which we set to 100 gigahertz by programming the wave shaper. And this is the phase response of the measured data versus of what we talk. So this is a very nice implementation of how you can do it with a two-comb in one resonator. In principle, now it's possible to do also in silicon nitride microresonators because with your waveguide dimension, you can also support several mode families, either in single polarization for terahertz devices or in a TETM mode for smaller. Okay, as a
Can you predict the spacing between the two modems in your simulations, or would you have to measure?
For silicon nitride, you can predict because there are few mode resonators, so our waveguides are few mode. In principle, you can calculate more. For magnesium fluoride, there are really multi-modes, there are 10 or 15 modes which can support Solitons in principle in a very good devices. But the difference is of a node of 100 kilohertz. So 600 or 300, that's why this RF spectrum are pretty compact. In silicon nitride, there will be larger difference. That's why your RF span will be much broader. And there will be possible overlap or wrap up around zero frequency, which is also a bit hard then to forecast. Triple comb generation was demonstrated in magnesium fluoride resonator. We did two combs in counterpropagating direction and one comb in copropagating. Okay, so the same scheme. So the result in optical spectrum is shown here. Green is comb which you can separate in one direction, and in the opposite direction you cannot separate because they're in the same kind of fiber. The RF bits again are very good. We are lucky in this case, obviously, because they do not overlap with each other, because both the central frequency and the FSR difference are very good. So all three combs are not overlapping. However, in the co-propagating scheme, you can observe this intermodulation, which is visible here, for example, in the bottom one and in the first one, but they are at least minus 20 dB lower, so you can kind of avoid them in the measurement. And there are some speculations on the possible applications for 2D spectroscopy, where you indeed can use three combs, and you can also do some very complicated schemes for distance measurement. However, it was, I think, never demonstrated in Soliton Microcombs. So if you want, you can realize this project. And then next topic is FMCW LiDAR. So again, but now this using Soliton Microcombs. In our group, we achieved, we demonstrated several approaches, not only with a single frequency laser, but with the Soliton Microcombs, mainly for FMCW in recent years. So Andrei discussed it a lot, so I won't repeat it. So for frequency modulated LiDAR, you need to have good linearity, and then you send your triangular short laser light to the target, then you beat with a reflected light, and in each pixel in each period, you can simultaneously measure the distance using this formula and the radial velocity using this formula. This has a big advantage because by doing single period, or for example, two periods with slightly different frequency, you can reconstruct both. You can calculate both the distance and the radial velocity of your target at this particular moment. Okay, there is a table comparison at different wavelengths. So all our measurements were done at telecom wavelength, but of course they can be extended to more interesting wavelengths, which we are heavily using now in commercial level. And this slide I skipped because you did some nice exercises before. So what is the node? Instead of a single frequency, we use all comb lines as a FMCW by doing the tuning of the pump. So as you may know, so to generate the Soliton, you need to offset your pump laser to specific detuning from the cold plate test. But then when you got the Soliton, you can scan the laser, your pump laser, back and forth within the Soliton existing range. And in fact, all your comb lines will follow the pump laser, more or less to the same tuning range, and of course the same frequency, and more or less with the same limit. That's why you can easily multiplex and use not a single line, but multiple lines. And then in principle, you can use them separately or in smart. However, there are disadvantages because when you scan the pump, if the Raman effect is present in your microresonator, there will be, first of all, change of the amplitude of your comp, but it's not that important for frequency modulated guidance. But what is not good, that the repetition rate will change, and basically the tuning of other lines will not be the same in terms of the tuning range and tuning linear. However, in our group, Anton and Johan, they use this method to demonstrate FMCW LiDAR with many comb lines. So again, schematically, you only tune your pump laser, and all comb lines will follow the same tuning pattern. We apply again triangular chirp to the pump, and we use several comb lines. Okay, you need to, in the easiest implementation, the multiplexers, and actually you record the result line by line by using the multiplexers. So you send your modulated comp as a local oscillator, and then you send it to the target, to the flywheel, and then the reflected light goes through the same collimator or another collimator. It goes to the balanced photodiode, and then you record the spectrogram and you do the short time Fourier transform, as Andrei discussed. So these are results for different comb lines. So the color coded are different comb lines at different frequencies, and they measured the spline rotating flywheel. This is the distance measurement. This is the radial velocity measurement for I think around 20 lines. What are the limitations of this method? As I said, so this is the chart, the Soliton existing chart. The crucial parameters are detuning, laser detuning, and the pump power. And with the pump power fixed, let's assume that there is no big change. You can tune only within limited range to maintain your Soliton. Otherwise, you will lose the Soliton, or you will jump in some breather state or modulation stability state, which are detrimental for you. That's why this range is actually limited. And in our real samples, it can be extended maybe up to 2.5, maximum 3 gigahertz, or more typically 1 to 2 gigahertz. So the tuning range is again limited, but not by your octator in this case, but the Soliton. So these are experimental data for individual comb lines. So at different tuning frequencies, at 100 kilohertz chip and 10 megahertz frequency chip, and you can see that to the first order, the tuning is the same in terms of range, and Johan and Anton, they performed a very nice measurement using only one scanning direction. So they use the grating, and then only scanning with the mirror in one direction to do the distance measurement of this EPFL logo. What are the drawbacks? Again, you need to, in fact, it's not fully parallel because you acquire your data one by one, so in individual channel, and using multiple photodiodes. Either you use single photodiode and you change the multiplexer, or use multiple diodes for individual lines. So it's a lot if you use 20 lines. But it's possible to improve it. So again, you need a local oscillator. And as a local oscillator, you use another comp with a slightly different repetition rate. In this case, it's not magnesium fluoride, it's back to silicon nitride. And the repetition rate is of an order of 500 megahertz. And you do the same, and then you beat on the receiver side with your local oscillator and do the coherent detection. and you superimpose all your channels on the single photodiode. And in this implementation, you need only single photodiode, okay, pretty fast, and a single data acquisition. And then you can reconstruct it from the single map, responding to your number of. And you don't need demultipliers, which is again -1 expensive, not expensive, but less. So again, the principle is the same. So you do the chirp of your pump laser frequency for both comms. They are slightly different FSR. You send it to your target, and you measure the through the circulator, the reflected light, and send it to the coherent receiver. And then you do the data processing. So it's exactly the same, but here your kind of channels, they are separated by the integer number multiplied by the FSR difference, which is 500 megahertz in our demonstration. And everything is the same. So you can calculate for individual comb line the distance and the velocity by analyzing this part of the RF spectrum. And what is important here, again, you need to, of course, separate your FSR in that way that your measurements, so and there is a limitation on the maximum distance, so you can't overlap because the FD and F down and F up corresponds to your distance. So the larger the distance, the higher these values. So, and the separation between channels is 500 megahertz, which is defined by the repetition rate difference. So there is a limitation on the maximum range you can measure, but with 500 megahertz, it's pretty large. And this is the actual, okay, a lot of theory. Let me show you some actual point clouds. So Anton and Johan, they did again the measurement of chest figures, and this is the spectrum of RF signal from the photodiode. This is the optical spectrum, and you see that these are signals from the reflected light in the individual channels. So this channel 1, channel 2 corresponding to different comb lines. And by data processing, offline data processing, you can reconstruct the profile, the shape of your chest, which is shown here. And they are about 28 meters apart from the collimator, but this is not free space propagation. There are, I think, 15 meters in fiber and then 10 meters in air. Yeah. And again, the radial velocity measurement are done by comparing the up and F down for many comb lines. And again, it's if you look at the all comb channels, they are pretty sensitive. And they correspond to the actual rotation speed of 250 of your rotating wheels. So in summary, Anton was able to demonstrate 64 channels with a 35 gigahertz station in the best case and the smallest case, and the acquisition rate is very, very high. So it's mega. Okay, so but still, you need to tune your pump laser inside the Soliton existence range, and we don't want to do it. So what can you do? First of all, this is the formula of the maximum laser cavity detuning. So after this, the Soliton will die. So it's proportional to the pump power, which you can increase, but not to the, yeah. And then it's inversely proportional to kappa naught. So if your resonator has a bad Q or it's very overcoupled, so your Soliton existence range is small. So the solution is to tune simultaneously the laser and the cavity, not just your laser. And then we call it feed-forward scan. So you simultaneously tune your cavity and your laser at the same frequency to the same rate. And then you can significantly, in principle, significantly extend your tuning range above 2 gigahertz. And you can do it in principle fast at megahertz rate. The solution again is piezoelectrical actuators, as Andrei demonstrated, as Andrei introduced in his talk. So again, we use either aluminum nitride or ZT material, and aluminum nitride is really capacitive. It has low leakage current, so low power consumption and high speed up to tens of megahertz, and it's very linear by default, so you don't need to do linearization. And that's what was demonstrated in the initial paper, where we tuned the soliton. So this is the soliton, and the piezo actuator is on top, and we apply voltage at 10 to actually 18 megahertz, and we measure the linearity of different comb lines, and they are pretty good. So, and here you can do a range more than 2 gigahertz, and in principle, you can do up to 1 megahertz. Also, it's possible to generate this slide, Andrei showed. It's possible to generate the Soliton Microcomb with self-injection on DFB. You don't need external laser, and then you can only apply your voltage to the actuator, to the ring, and you don't need to tune your pump to be able to tune within 1 or 2 dB. If you want to tune more, you need to again simultaneously tune the resonator and the pump. The last slide for today and for the whole workshop is additional approach, where actually it's not a frequency modulated LiDAR, it's chaotic microcomb parallel coherent region. There are previous work where they use amplitude modulated laser to single frequency laser to measure the distance. And our achievement here that we use not a single frequency laser, but multiple comb line in a noisy state. So this is the first application of not Soliton, which is like holy grail and the most desired state in frequency comps, because the optical lines are phase locked. In fact, this is the first very useful application of noisy comps. So the regime which is easily accessible, and it has advantages of much higher power per line. So this is the RF bit node between comb lines. So you see that they are not coherent. So the bit node is kind of broad up to several gigahertz. And in this scheme, you again use one Soliton comp as oscillator and then one noisy comp as a signal. And then you do the cross correlation between two measurements in this scheme. And this is the formula which can again provide you the distance and the velocity for individual channels by calculating the cross correlation between this signal from this photodiode and this. So this is just a local oscillated bit with a local oscillated Soliton comp, and the bottom signal is actual reflected signal from your tap. And the funny part here that in previous demonstration, the distance resolution is defined by your frequency chirp range, which is orthogonal 1-2 gigahertz for our scheme. And here in this slide, the distance resolution is inversely proportional to the bandwidth of your noise. So the noisier your bit node is, the better your distance resolution. So in fact, our comps and the noise properties, they depend also on the detuning a bit, and you can reach the same 2 or 3 gigahertz noise property. So the distance resolution is kind of the same as on frequency modulated comp LiDAR, but this device is kind of easier to access. You don't need Solitons for this. That's it for my talk and for the workshop. Thank you for your attention.
Question? Thank you. Please stop Grigorii in the hallway. I just want to show you a quick thing before lunch.
You want to show that first, or can I? Is this the? Yeah, this.
So for lab tours,